Identifying rotations, 9.3a. We have 4 previous videos for Chapter 9 that are in the geometry playlist in the description. So remember that a rotation is a transformation that turns a figure around a fixed point called a center of rotation. And a rotation is an isometry. So the image of the rotated figure is congruent to the pre-image. It doesn't change in size or shape, but it will change its orientation. So this figure rotated to this place. See? It's like it rotated around a point that was right here. This is not a rotation. We can imagine there's a line of reflection here. That would be a reflection. So we can identify rotations by seeing if they appear to turn around a point. If this blue one rotated around, then this big bumpy side right here on the left would still rotate around to be on the left. It wouldn't be on the right. See, that's a reflection. And we can construct a rotation by using tissue paper. We draw a triangle and a point on a sheet of paper like this, and we put a piece of tissue paper on top of that triangle and point and trace them, okay? So that's what I did. You just put them on top like that, and you trace it right through the paper, okay? Then we can hold our pencil or our finger and rotate the tissue paper counterclockwise. You could even do it clockwise if you want to. It doesn't have to be counterclockwise. But for this example, we're going to do counterclockwise. So I move it like this, and now I can see the triangle again. So I'm going to trace this one. So I'll have 2. So we trace a new triangle on that tissue paper, and we draw a segment from each vertex to the center of rotation, to our black point. And our construction should show that a point's distance to the center of rotation is equal to its image's distance to the center of rotation. And the angle formed by a point, that center of rotation, and its point's image is the angle by which the figure was rotated. So if we go with the top vertex for each one with those segments, inside here would be the angle of rotation, okay, for the pre-image and the image. So a rotation is a transformation about a point P called the center of rotation, such that each point and its image are the same distance from P, and such that all angles with vertex P formed by a point and its image are congruent. So here we have point P, and we have a pre-image A, and it was rotated to this point A prime. An angle APA prime is the angle of rotation. And if we measure the angle with a protractor, we see it's 50 degrees from here to here, about that point. And the hands of a clock rotate around the face with a center of rotation where the hands connect in the center, right here. And a Ferris wheel, or any wheel, rotates with a center of rotation at the axle. An ice skater rotates as they spin in place, like this, with a center of rotation vertical from their head to toes, okay? And the spinning earth rotates around a center of rotation as its axis. So the center of rotation here is coming straight down through her body as she's spinning around like this, and the spinning earth, it's on a tilt, that's why we have our seasons, right? It's spinning around the axis, see? Okay? We can draw the rotation of a triangle about a point P by measure of angle A, whatever the measure of angle A is. So for our triangle and our point, we draw a segment from each vertex to point P. We use a protractor to construct an angle congruent to angle A. So we measure it, we see it's 60 degrees. What we do is we do each segment from this bottom segment, we make a 60-degree angle to make ray number 1 right here. From the middle segment, we make a 60-degree angle to make ray number 2 right here. From the top segment, we make a 60-degree angle to make ray number 3. So now we have ray 1, 2, and 3 up here. We measure the distance from each vertex to point P and mark off this distance on the corresponding ray to locate the image of each vertex. So for this bottom one, this one is 6.5 centimeters, This number 1 ray is the corresponding one, so I put a point at 6.5 centimeters. This one is 4 centimeters, I put a point at 4 centimeters. This one's 7 centimeters, I put a point at 7 centimeters. Then we connect the images of the vertices, just connect the dots, and our blue triangle pre-image has rotated 60 degrees about point P to the pink triangle image. That's a 60-degree rotation. See? We did each segment, measured the distance of the segments, and put that on the rays to make our image. Okay? And if we rotate a teardrop 45 degrees, if we do it 8 times, we'll make a flower. We just go 45 degrees, all the way around. It'll actually make a symmetrical flower. And the center of rotation may be inside or outside the figure. So for this hand, it's got a magnet underneath here, right in the middle, see? That's the center of rotation. And the pink dot is the center of rotation for this square. So if we turn it 45 degrees, it'll look like this. If we turn it 90 degrees, rotate it 90 degrees, it'll look like this, which might fool us into thinking it went back to its original position. But if we put a picture or something on one of the corners here and we rotate it 90 degrees, we can see that it did not go back to its original position. It looks like it did, okay? So all the sides of a square are the same length, so it appears to have gone back to its original position, but marking it like that will show us it didn't. And this pink dot is the center of rotation for this square, so it's not inside the square. This square is going to rotate about this point like this, see? Okay? And take a look at this E. Where will the E be if it rotates 90 degrees counterclockwise? Well, it's on a coordinate plane, and lucky for us, the x and y axis are perpendicular to each other. That means that's a 90-degree angle, doesn't it? So, where will it be if it rotates counterclockwise 90 degrees? It'll rotate like this. It'll come down, and it'll be here. See? And look at this letter A. If the A rotated clockwise 90 degrees, where did it rotate from? So this one already rotated. So if it rotated 90 degrees clockwise to go back to its original position, we need to go counterclockwise 90 degrees. So this one will go up here, won't it? And that's where it was when it started, okay? And take a look at this. This is a yin and yang, and it's in Chinese philosophy. I'll have a link in the description if you want to know more about it. If we rotate the yin and yang 180 degrees, whether clockwise or counterclockwise, the black side, the yin, will be on the left. See? Look at how these are lined up vertically. We would just make it so the white one was on top, the white dot was on top, and the black dot was on the bottom. And now the yin is on the left and the yang is on the right. See? In Chinese philosophy, they represent dark and bright, or negative and positive. It's like the balance of life. Okay? So pay attention to the direction of the rotation, whether it's clockwise or counterclockwise. If you don't pay attention, you could rotate a figure to the wrong quadrant of the coordinate plane, and it'll be wrong. So it's really important, okay? Be diligent about the direction, okay? We're going to finish up lesson 9.3 with drawing rotations in the coordinate plane. Then we're going to move on to 9.4 about compositions of transformations and glide reflections. Then we're going to do symmetry and finish that with solids of revolution for 9.5, okay? So hopefully you really understand rotations now, and we'll be able to keep moving forward and learning about other transformations, all right? I hope you have a great day, and I'll see you next time. Bye.